Hello everyone, let's solve our next problem. Let S be the set of points whose coordinates x, y, and z are integers and satisfy x between 0 and 2, y between 0 and 3, and z between 0 and 4. Two distinct points are randomly chosen from S. The probability that the midpoint of the segment they determine also belongs to S is m over n, where m and n are relatively prime positive integers. Find m plus n. Okay, interesting. So we have a three-dimensional lattice of points. It's bounded. My first instinct here, I guess, is to figure out all possible endpoints of such a line segment such that their midpoint is also one of the coordinates in this set. There's a lot of points in this lattice. So one thing we're going to do for sure before we really get into the details is compute just how many points there are in this lattice. There's a lot of restrictions that we can put on the... Oh, you know what? Here's another thing to think about. If the midpoint of this segment is itself also a lattice point, then this sort of property of the midpoint being in the set has to hold for each coordinate individually. So in some sense, well, it's not quite easy. It's not quite as simple as just computing the probability of this occurring for each individual coordinate and then sort of multiplying them together, because even though two distinct points are randomly chosen from the set, they could, for example, have the same x coordinate, but in a lower dimensional version of the problem, that wouldn't be the case. What I might try and do is work this out for the two-dimensional problem where we ignore the z coordinate and see if I can find a way of simplifying things in 2 dimensions that should also work in 3. Like this seems like it's going to turn into some kind of counting problem where let me draw a little bit of a picture here to explain how I'm interpreting the question. So the cardinality of S, the number of points in S, is going to be equal to 3 times 4 times 5, which is 60, right? There are 5 possible values of z, 4 possible values of y, and 3 possible values of x. So in a two-dimensional version of this problem, I'm going to ignore the z coordinate for a moment. So this is what the problem looks like with only the x and y coordinates. We have to choose a pair of points at randomly. So that can be done in 12 choose 2 ways. And let's break it down one point at a time and see if we can come up on conditions of the coordinates such that the property works. If this is one of the points, then the other points in the pair that work, like, let me highlight it. If that's going to be one of the points, then only these 3 points end up working, right? Because let's say, if this is the point that's in the pair, the midpoint is not in the set. If this is the point, then the midpoint is not in the set. But if I take this one, for example, then the midpoint is in the set. And in fact, we can count all of the possible line segments that would work, right? So I can draw all the possible line segments that work for this. 1, 2, 3, 4, 5, 6. I mean, I know I'm not drawing line segments, but I'm drawing the pairs of points which would satisfy this property. And then we have the same thing if we take that entire grouping and move it up. So there are 12 pairs that work. So in 2 dimensions, the answer is 12 divided by 12 choose 2. So this is 2 out of 11. Now, will I be able to do something easily like this in 3 dimensions? I mean, visualizing it might be difficult. There are going to be, you know what I'll do? Let me redo the problem again, except using the y and z coordinates. So basically the same thing except with more dots. I'm just trying to get, some intuition for how this counting procedure will scale. So now the total number of pairs is 20 choose 2. And how many of them will actually work for the for this counting procedure? See, now I have this square that I drew before, and any translation of that thing will work. So maybe this is a way of doing it, is these points are all within a distance of 2 from each other in some kind of an infinity norm. So maybe what I do is count how many points satisfy this that are within some norm of each other, and then sort of work out the translations, and then do the same thing for a larger norm, right? Because you can see, let me get rid of, well, take this point as a reference point, and if you repeat this diagram and just translate it so that the reference point is now here or here, how many of this sketched figure, how many possible locations could I put that according to where the top left point is? Well, any of these points could be the top left point of a figure like that. So, what am I trying to say here? Basically, what I did up here, I took my figure and I realized that there were 2 copies of this figure which work. There's the one that I've drawn, and there's one that's shifted up by a distance of 1. Here, there should be 6 in total. There's the one that I've drawn, and then there's also one for each of these points. So I can shift this figure to the right once, or to the right twice, and I can shift it down once, down and right, and down, right, right. So there are 6 of these. And that's when we're looking for points that are within 2 of each other in an infinity norm, or in a soup norm. Now there will not be any resulting figures that are exactly a distance of 3 in a soup norm. So if I take this point as my reference again, the top left point, these are the points that are a distance of 3 away in a soup norm, but you can kind of visualize just by connecting them all to the point in the top left that none of them will have a midpoint in the set. So we need to look at points that are a soup norm of 4 away. And so that'll be this one. This one will work. And I can also do this. And now if I want to think about how many ways I can repeat this diagram it's this one, or I can shift it down by 1. And those will all work. So I think what I'll do is this is how I'm going to try and attempt it in 3 dimensions. I'm going to count from one point, say the bottom, like say the origin. How many line segments are there that work where the line segment has a length of 2 in an infinity norm? And then ask myself how many translations of that figure will also work, and then do the same thing for the 4 norm. Okay, it might be hard to draw a picture for this. And I guess I'm not really, if I think of this as being the origin here, I do have other points that I've drawn. So I don't want to double count, and I don't want to undercount when I do this. So what is a good way? So the number of possible segments is 60, choose 2. Okay, what I'm going to do is I'm going to draw this in 2 dimensions, where into the screen is the Z direction. So this picture should look exactly the same as the original one I drew. Okay, so that makes this point here the origin. And you know what I can do? Let's take this as the reference point for now. We know that there are 3 line segments that work like this. And Z is between 0 and 4. So for this line segment, I'm really capturing 3 different line segments here, because a Z coordinate of 0, 2, or 4 will work. Same with this one. The Z coordinate could be 0, 2, or 4, and this one, the Z coordinate could be 0, 2, or 4. What I am missing is the fact that there are two line segments that are like projecting to a point here. All right. You know what another way of doing this is okay, so let's say, so what I've just realized is if I choose any point, so let's say this is the origin, draw a cube of side length 2. Okay? So I've got a cube of side length 2. That all of the vertices of this cube will be in the original set S. And all of the midpoints of these edges and face diagonals and body diagonals, they will all those midpoints will be in the set S, right? If I connect the very front face diagonal like this, its midpoint will be in the set. If I connect opposing diagonals like that, it'll be in the set, the midpoint. So then what I'd like to ask is, how many cubes of side length 2 can we fit inside? But then I don't only need cubes, I also need rectangular prisms. But there, it's possible that one of the side lengths is not even. Oh wait, no, but then then there might be a double counting thing happening by accident. Goodness, this problem is a bit, it's kind of harsh problem. Starting to wonder if, rather than trying to visualize things and draw everything, maybe if I just work out like purely combinatorially, right? Like you're choosing, you're simply drawing numbers out of a hat here, right? I think this cube approach will work. Sort of, except that I'm going to combine two ideas I've had already. One is drawing this cube, counting how many line segments it contains that are successful, and then counting how many ways I can translate the cube around. That will capture all of the pairs that are distance of 2 apart in the soup norm. Then if I do the same thing that are distance of 4 apart in the soup norm, like that are exactly 4 apart in the soup norm, I won't have to worry about different size rectangular prisms. Yeah, this is how I'm going to do it. Okay, so 1 cube. How many line segments does this contain that are successful? Well, there's going to be edges. There's going to be face diagonals, which is 12. Right, there are 6 faces, and each face has 2 face diagonals. And I don't know what the term is. I'm going to call it a body diagonal. There are 4 body diagonals that connect completely opposing corners, right? So what is this? 24, 28. So 1 cube of side length 2 contains 28 good segments. So here's a problem. I'm going to double count here. Did I end up double counting up here earlier in my much earlier thing? I did, didn't I? No, not in this case, and not in this case either. Because if I shift this in the x direction by 1, actually I can't, right? This thing is, I'm going to draw a picture to remind myself what this looks like. Okay, so I cannot shift in the up direction. If I shift in the y direction upwards, it's fine. I shift it into the screen by 1 in the z direction. That's fine. I won't be double counting. But then when I shift it again, I will end up double counting. But I should only have to remove 1 face worth of points. Okay. Okay, I've got a cube of side length 2, 28 good segments. And how many ways can I repeat that cube and shift it around? So there are 4 such cubes. I take this one sort of base at the origin. I can move it 1 unit up in the y direction. So that's 2 cubes in total. but I can also shift it into the screen, excuse me, in the Z direction. That's a third. Then I can shift it in the Z and the Y direction. That's a fourth. But then when I shift it twice in the Z direction and try to count them all again, what I have to do is I have to remove that face. So I have to remove 6. Okay. 4 such cubes. Okay, and I also have and then I'll say 22 good segments on 4 more cubes. Okay, so segments of length 2 is 28 plus 22 times 4, which is 200. And when I say length 2, I mean in the infinity norm. Okay. There will be no possible points of length 4. Of length 3. So now we consider length 4. So again, I'll start at the origin. I'm going to draw a cube, but the points that work will no longer be restricted to the vertices of the cube, or the points involved. How big should I draw this? Okay, I'm going to draw it small. Hope it doesn't get too messy. So this is now a cube of side length 4. Wait a minute, I can't draw a cube of side length 4 in this thing because x is between 0 and 2. So what I need well, if I'm choosing pairs of points, they either have the same x-coordinate or different x-coordinate. If they have the same x-coordinate, then we're basically in the case of only thinking about y and z being distinct. And we've kind of solved that problem, or at least I drew a picture of it above. And if they have different x-coordinate, then those two coordinates must be 0 and 2. So maybe I break it down into those two cases. I still want I want to only count the ones of length 4. So if the x-coordinate is the same, this picture that I've drawn here, with the crossings, that can also be shifted down by 1. That'll give me another 4 valid pairs. So there are 4 times 2 times 3, which are 24 ways, 24 pairs of length 4 where the x-coordinate is the same. So the only thing we have left to count is the number of length 4 segments where the x-coordinate is not the same, but that means the x-coordinates must be 0, 2 or 2, 0. I think that's just 4 times 2 times 2, right? So if I take this picture, really just imagine that I grip this point and that point and pull them out of the screen by a distance of 2 to represent the different x-coordinate, so that this has an x-coordinate of 0, and now this, pulled out of the screen, has an x-coordinate of 2. Then I just repeat this diagram. I have this one and I have it also shifted down, but then I just sort of reverse those two things. What is this? This is 16, right? I think that counts them all. I've spent quite a lot of time on this problem already, so I'm kind of confident and comfortable that I've counted everything now, and I'm willing to sort of lock in my final answer, I guess, and then if I'm wrong, I'm wrong. But what is my absolute total here? I have 200 plus 24 plus 16. $240. So the probability is 240 divided by 60 factorial times 2 factorial times 58 factorial. 240 times 2 divided by 60 times 59. 8 over 59. And so if we go all the way back to the question, m plus n should be 67. Yeah, I don't want this video to go on forever, so I'm gonna say that this is my answer. But in terms of my approach to this problem, I mean, there very well may be a nicer way of doing this from like a combinatorial approach on the coordinates of the points themselves. If you think of the points as being randomly sampled without replacement, and thinking about how many possible pairs satisfy this condition. But I think this geometrical way works, right? By writing this cube, or by drawing this cube, you know, there's 4 copies of this cube where all of the segments are counted, and then there's 4 more copies of the cube where you have to remove the front face worth of segments, and those are simply because the front face of those segments just correspond to the back face. The back face of those segments shifted by a distance of 2. So that's why I removed those 6 when I did this. And this should count all of the possible line segments of length 2. And then just do the same thing, a similar counting procedure where you count all the line segments of length 4. And assuming my argument there was correct, then I don't know at this point where I possibly could have gone wrong. Maybe some arithmetic or something like that. Anyway, this will be my answer. 8 out of 59 is the probability. Seems like a strange number, actually, the fact that there's a 59 in the denominator. I mean, I know it comes from the factorial, but I would have imagined a nicer denominator in the probability. Final answer is 67 then. And if I find a mistake, or if I have any more to say about this one, I'll put it down in the description. Thanks for watching.